Imagine needing to quickly pinpoint critical information from thousands, maybe tens of thousands, of complex documents. And maybe you're looking for something incredibly rare or really subtle. Now, picture that scenario, but in medicine, where even a tiny misinterpretation in a patient's report could have really serious consequences. How do we ensure AI systems are not just fast, but deeply accurate and understandable in these high-stakes fields? Our mission today isn't just about explaining some new AI method. It's really to show you why medical AI that thinks more like a doctor using structured knowledge rather than just crunching numbers might be better at finding those rare diseases. The ones even advanced large language models sometimes miss. This approach offers a kind of clarity, maybe even trust, where those typical black box systems can feel a bit opaque. So today we're diving into some really fascinating research. It's from Felix Mutzel, Misha Dabrowski, and Bernhard Kainz. Their paper is called Ontology-Based Concept Distillation for Radiology Report Retrieval and Labeling. And it proposes this novel ontology-driven way to compare medical texts.
It really could change how AI interprets radiology reports. So stick with us, and you're about to get a shortcut to being well-informed on this really exciting development. Okay, so let's unpack this a bit. When AI systems are trained to analyze medical images, like, say, a chest X-ray, they often rely on the text that comes with it, those detailed radiology reports, to understand the conditions. The most common method for comparing these reports involves converting them into these complex numerical representations called embeddings.
Right, embeddings, generated by powerful models like CLIP or CXR-BERT.
Exactly. They basically translate words, sentences, into points in this huge mathematical space. But what are the actual downsides to this approach, especially in medicine?
Yeah, that's a really critical question, because while these embedding methods have done some impressive things, definitely in more general tasks, they hit some significant hurdles in a medical context. The biggest issue, I'd say, is their black box nature.
Meaning you can't easily see why it made a decision.
Precisely. It's incredibly difficult to interpret the reasoning. Why did the AI say these two reports are similar? The embeddings themselves are, well, opaque. You can't easily trace it back. And on top of that, they're often computationally very expensive, need a lot of resources. But maybe the most crucial point is that they weren't really designed with the very structured, very nuanced nature of medical knowledge in mind. Medical information isn't just a random collection of words, right? It's this intricate web of concepts with precise definitions, hierarchies, relationships. So, in healthcare, where clarity, precision, interpretability, these things are paramount. These opaque methods might not be the best we can do, especially, as you said, for identifying those rare or long-tail conditions that need very specific understanding.
That makes perfect sense. It's almost like trying to find a specific rare bird using just a general birdsong detector. You'll probably catch a lot of common bird songs, but that really specific nuanced call of the rare one, it could easily get lost.
Exactly.
Generic text embeddings are kind of looking for statistical patterns, maybe not the deep semantic meaning a human expert would pick up in a report.
Yeah.
So if we want to move beyond these black boxes and really get to that semantic truth, what are the researchers actually proposing?
Right, and that's precisely where their ontology-based method comes into play. Instead of just looking at, surface-level word patterns, they're digging much deeper into the actual meaning of medical concepts and how they relate to each other.
Okay, so less pattern matching, more like conceptual understanding.
You got it. And to do this, they leverage something called the Unified Medical Language System, or UMLS.
UMLS. Can you maybe give us a quick rundown for listeners who might not know what that is?
Sure, absolutely. Think of UMLS as this incredibly vast, highly structured library of medical concepts. It's like a master dictionary and thesaurus combined, but for the entire medical field. Within UMLS, every distinct medical thing, whether it's an anatomical part like lung or an observation like pneumonia, gets linked to a unique code. A concept unique identifier, or CUI.
A CUI.
Yeah, and this allows a whole radiology report to be represented, not as some fuzzy numerical embedding, but as a clear, interpretable set of these CUIs. These are clinically grounded medical concepts, and they come with their definitions and all the relationships that UMLS already maps out.
So once you have these CUIs representing the report, how does that make the AI's understanding more transparent? What's the real difference compared to that black box output?
The key difference is traceability, really. Instead of just getting an output saying, These reports are 70% similar with no explanation.
Yeah.
You get this clear, semantically rich breakdown. You can see exactly which medical concepts are present in each report, how they might relate. It's like seeing the medical ingredients.
Right, you can see the building blocks.
Exactly. It makes the AI's reasoning so much more understandable and, crucially, more trustworthy, which is just essential in a clinical setting. You can actually audit the AI's thinking process, so to speak.
That transparency really does sound like a game changer. So, okay, how do they actually do it? How do they go from, a complex free text radiology report, those dense paragraphs radiologists write, to these precise, standardized sets of medical concepts? What's the actual process?
They've laid out this pretty sophisticated 4-part methodology. It systematically breaks down and standardizes all that information. The first stage is what they call a robust entity extraction pipeline.
Entity extract. Okay, sounds like it's pulling out the core medical facts, the important bits. How does it manage that from all that natural language text?
Precisely. This pipeline meticulously pulls out mentions of medical entities, things like specific anatomies, lung, heart, or observations, consolidation, effusion. They do this by taking existing really good tools, specialized language models like RadGraph-XL and SapBERT, which are already trained to understand complex medical jargon, and enhancing them.
Enhancing them how?
Well, a critical improvement they made involves intelligently handling negations. This is super important in medicine. For instance, in a phrase like, no consolidations observed in the left lung, a simpler system might just pull out left lung. But their pipeline correctly identifies left lung as being part of a negated observation, meaning that finding consolidation is not present there.
Ah, that's crucial. You don't want the AI thinking something is present when the report explicitly says it's not.
Exactly. It addresses a really common and potentially dangerous pitfall. Then they link these extracted entities, including their negation status, to their unique CUIs using SapBERT. And they carefully limit the vocabularies they map to, using comprehensive structured sets like SNOMED-DCT-US. That's a widely used clinical terminology system. That limitation is actually key for consistency.
Okay, so it's not just keyword spotting. It's understanding the clinical context like negation and assigning these standardized, unambiguous UMLS CUIs. So the end result of this first step is that each radiology report gets transformed into this distinct, machine-readable set of CUIs representing its core medical content. What's step 2?
Step 2 involves constructing a knowledge graph. They build this directly from the vast network of relationships already defined within UMLS. Now, this graph focuses particularly on hierarchies like pneumonia is a type of lung disease and semantic closeness. While they mention you could use this graph for initial candidate retrieval in huge datasets to speed things up, its really crucial application here is for synonym discovery.
It's synonym discovery.
Yeah. If a CUI from one report, say for a specific finding, can reach a CUI in another report set just by following synonym links in this graph. The system recognizes them as essentially the same concept when comparing the reports. This ensures a much more accurate semantic match, even if slightly different terms were used. Interestingly, they found that trying to use all the semantic distances across the entire graph added a lot of computational complexity without really boosting performance much, so this focused synonym approach was more effective.
That sounds incredibly precise. Okay, so now you have these meticulously curated sets of medical CUIs for each report. How do you actually measure how similar two different reports are? Because like we said, similarity isn't always simple.
Right, and that's where the core of their comparison logic really lies. They propose using a modified version of the Tversky Index. The Tversky Index is actually a powerful generalization of more common set similarity metrics like Jacquard or DICE.
Okay.
And this brings up a really interesting point about how we humans perceive similarity. Cognitive psychologist Amos Tversky did studies showing our similarity judgments are often asymmetric.
Asymmetric. What do you mean by that in this context?
Well, think about it. We might readily say, for example, that a specific diagnosis like lobar pneumonia is similar to the broader category pneumonia because it's a type of it.
Okay.
But we're probably less likely to say the broad category pneumonia is similar to the specific lobar pneumonia. The direction matters.
Right, the scope is different.
Exactly. Their method cleverly accounts for this asymmetry dynamically. It looks at which set difference is larger and gives more weight, effectively, to the more prototypical concept. And crucially, they also add in what they call a contradiction term.
A contradiction
Yeah,
term.
this actively penalizes reports that contain contradictory information. So if one report explicitly mentions pneumonia and another explicitly mentions no pneumonia, using those negation flags we talked about, their method makes the dissimilarity score between those two reports much, much higher. It effectively flags conflicting findings.
Wow, that's a fantastic feature. Not just looking for shared concepts, but actively identifying when information clashes. That seems vital. And it gets even more refined with something called a preference vector, right? How does that work, and why is it so useful for clinical applications?
Ah, yes, the preference vector. This is what makes the similarity measure task adaptive.
Yeah.
And that is incredibly powerful in a clinical setting. It essentially lets you filter or rank the importance of different semantic types depending on the specific clinical question you're asking.
Can you give an example?
Sure. Let's say your task is disease localization, finding where the problem is. In that case, a report mentioning lower left pneumothorax and another mentioning lower left pneumonia might be considered highly similar because they share the same anatomical location lower left.
Okay.
But if your task is disease detection, just finding if a certain disease is present, then maybe lower left pneumothorax and upper right pneumothorax become more similar. Why? Because they describe the same underlying disease, pneumothorax, regardless of the position.
I see. So you can tune the definition of similarity.
Exactly. This fine-grained, context-aware similarity where you can literally adapt what similar means based on what matters most for the doctor or patient at that specific moment.
Yeah.
That's absolutely crucial for building AI tools that are genuinely useful in the clinic.
That ability to adjust the definition of similarity on the fly, tailored to the specific clinical question.
Yeah. That feels like a huge step forward.
So once they built this whole sophisticated pipeline entity extraction knowledge graph, the adaptive similarity metric, how do the researchers actually check if it worked? How do they validate it?
Right, the validation. They put it to the test by applying it to two key tasks using a well-known large dataset called MIMIC-CXR. MIMIC-CXR is this big collection of chest x-rays and their corresponding radiology reports. It's real-world medical data widely used for exactly this kind of validation. The two tasks were, first, retrieving relevant reports based on similarity, and second, generating robust disease labels directly from the reports.
Okay, so crunch time. After all this sophisticated structured analysis, what were the results? Did this ontology-based approach actually make a tangible difference compared to the standard methods?
The results were genuinely compelling, quite impressive, actually. Zooming out a bit, let's look at the first task, radiograph classification, which relies on retrieving similar reports. They used MIMIC-CXR for this. Their ontology-based approach, specifically using a method they call prototypical retrieval, significantly outperformed the state-of-the-art embedding-based methods, the CXR-BERT and CLIP models we mentioned earlier.
Significantly outperformed how? Like in terms of numbers?
Yeah, so they measured performance using the area under the receiver operating characteristic curve, or OROC. It's a standard metric for classification tasks, basically measuring how well the model distinguishes between different conditions. Higher is better. Their method achieved a mean OROC score of 0.741.
Okay. And how does that compare?
Well, CXR-BERT got 0.711 and CLIP got 0.702. So 0.741 is a noticeable jump. It clearly demonstrates that for those tricky long-tail medical tasks, those rarer but critical conditions, these domain-specific interpretable methods, powered by structured knowledge like UMLS, can actually beat the more general, opaque text embeddings.
That's a really significant improvement for retrieval, especially where those subtle, rare conditions really matter most. Impressive.
But you said they also use their pipeline to generate new disease labels for the MIMIC-CXR dataset itself, right? Based on the ontology. What did that show?
Yes, and this is perhaps even more fascinating. These newly generated labels, particularly when they used their containment retrieval method, achieved an even higher mean AUROC score, 0.8802.
Wow, 0.802.
Exactly. This not only showed how accurate their labeling pipeline was, but it also outperformed several modern large language model-based methods. We're talking models like Llama 3.3, DeepSeek 2, Medgemma.
So better than some of the big LLMs at labeling these reports. At this specific structured task, yes. It even improved classification performance for certain conditions like pleural effusion and pneumothorax compared to the original TextBERT labels for MIMIC-CXR, which were themselves generated by expert rule-based systems interpreting radiologist annotations. It really highlights how even very sophisticated general-purpose LLMs can sometimes struggle with the absolute absolute precision and the highly structured nature required for accurate medical reporting. That's where these ontologies, with their unambiguous, clinically validated definitions, truly shine.
So this really isn't just about getting slightly better numbers in a research paper. It's pointing towards making AI in medicine more reliable, definitely more transparent, and ultimately just more useful for clinicians and patients. It suggests a future where AI could genuinely help doctors make more accurate diagnoses, maybe faster, especially for those really hard-to-spot long-tail conditions. So to wrap up, we've really explored how digging deep into the structured world of medical ontologies like UMLS can potentially revolutionize how AI understands and processes these complex radiology reports. It offers a potentially clear, interpretable, and based on these results, maybe even superior alternative to those traditional black box methods, particularly for those tricky, rare conditions that often get overlooked.
Absolutely. And I think ultimately this research isn't just about improving medical imaging AI, though that's huge. It kind of serves as a blueprint, maybe, for any field where AI precision and trust are absolutely paramount. It really makes us consider a broader principle, doesn't it? How much more effective could our AI systems be across the board if they consistently integrated the rich, structured domain knowledge that often already exists in a field, rather than just trying to learn everything from scratch, from raw, unstructured data alone? This work really demonstrates the power of embedding that human-curated expertise directly into the AI's foundational understanding.
That's a great point. So as you reflect on our deep dive today, maybe consider this. How many other fields beyond medicine could benefit immensely from moving past these generic data embeddings, truly embracing their own specialized ontologies, their own structured knowledge? What crucial details, what hidden relationships might we be missing right now in other complex data sets simply because we're not leveraging this kind of structured domain knowledge? Something to think about.